Problem number 40. Draw three resonance structures for the nitrate anion, NO3-, that contain a central nitrogen atom. So this is a polyatomic anion. To draw the three resonance structures, we need to first draw the first resonance structure, which is basically to draw a Lewis structure for this formula. So that's your first job. Just draw a Lewis structure and then see if you can draw two more of them, okay, where the atoms are connected the same way. So that would be the three resonance structures. Let's just get the first one. That's the major hurdle. And then once you have the first one, getting the other resonance structures is usually simpler. Okay, so here we have a nitrogen, 3 oxygens, and don't forget that extra electron, the negative charge. So here are the pieces of the puzzle. Nitrogen has 5 valence electrons because it's in group 5A down there. Group 5A, and then oxygen is in group 6A, so it has 6 valence electrons, and that's what the oxygens are like. And then here's that extra electron that will need to go in the structure somewhere. Let me get rid of this periodic table here to give us more room. Now think symmetry. Nitrogen, you got 1 nitrogen, 3 oxygens. The oxygens are going to surround the nitrogen, and the problem even tells you that you have a central nitrogen atom. But if it didn't say that, you should put nitrogen in the center for the sake of symmetry. So let's put nitrogen in the center, and we're going to surround it by the 3 oxygens. Okay, like that. So here, let me put the electrons on the nitrogen. Let's also put the electrons on the oxygens. And notice how I'm pointing the unpaired electrons towards each other so that they're ready to bond up. And here I'll put that extra electron over here just so we can use it when needed. Okay, now normally when you're drawing Lewis structures, you try to use the common bonding patterns. Okay, nitrogen, the Lewis dot structure for the atom has 3 unpaired electrons. So nitrogen typically forms 3 bonds. It could be 3 singles, or maybe a single and a double, or maybe even a triple. Okay, that's what you will normally see nitrogen do. And oxygen, with its 2 unpaired electrons, likes to form 2 bonds. Maybe it's 2 singles or a double. But that's the common bonding patterns, but not always. And some of the exceptions that you'll see to these common bonding patterns occur when you have polyatomic ions. Okay, the presence of the extra electron can disrupt the common bonding patterns. So, don't use this as an absolute constraint. In other words, let's just do what we have to do to connect these atoms. Okay, so first step first, let's go ahead and connect the atoms together and see where that takes us. So we'll form a bond between these two. Whoops, let me get that a little neater. Form a bond between those two, and those two. And let's go ahead and take this electron. Let's put it somewhere. Okay, it doesn't look like it can fit on the nitrogen because nitrogen already has an octet, but the oxygens each have 7. So looking at this oxygen, 1, 2, 3, 4, 5, 6, 7. So they all got 7. They could use another electron. You only got 1 more. So let's just take it and let's move it over to, say, the oxygen on the right. Okay, there we go. All right. Now, how do we fix this situation? Um, okay, how do we fix that situation? Well, one creative thing would just be you take these two electrons and you connect them together. You form like a bond between the two oxygens. But uh, that's a bad solution for a couple reasons. That would disrupt the symmetry. And also, the second bad reason is having a ring with just three atoms is very unstable. It's very unstable. It can happen with carbons sometimes, but that's something that you would see more in organic chemistry. But it's very rare, and you shouldn't look for that type of solution. So think symmetry. Um, anyway, let's take. How about this? Let's take uh, this electron and one of these electrons and form a double bond. So let's take this one and that one over there and form a double bond. And how about now looking at nitrogen, though? First of all, nitrogen has more than an octet. So nitrogen has more than an octet, but this oxygen still has its 7. So let's take this electron, let's bring it down here to that oxygen. And we'll put it down there. Okay. We'll put it down there. Now, this is a good Lewis structure. We are unable to draw the Lewis structure if we're constrained to use the common bonding patterns. Okay, but this is a non-common bonding pattern for nitrogen. Notice that it has 4 bonds, a double and 2 singles, okay? It has 4 bonds, but it keeps its octet. That's the important part. The octet rule must be satisfied for nitrogen and oxygen and carbon. So I'll say that up here. Carbon, nitrogen, and oxygen. The octet is a must. Octet. Okay. Always satisfied. So you might have to break the common bonding patterns to get the Lewis structure, but make sure you keep your octet. And looking, everybody has an octet here. This oxygen, 2, 4, then 6, 8, so an octet. This oxygen here, 2, 4, 6, and the bond makes 8. That one's also 8. Nitrogen's also 8. Now notice that these two oxygens are also in a non-common bonding pattern. Oxygen typically forms 2 bonds, 2 singles or a double, but these, they're only 1 bond. Again, we had to disrupt the common bonding patterns in order to get it done. So they still have their octet. Now, because this is a polyatomic ion, the structure is negatively charged. We acknowledge that by bracketing it and putting a minus charge out here. So you'll normally see resonance structures for polyatomic ions like that. A lot of people forget to do that sometimes. Okay, so that is correct. I'm going to put a check mark above that one. And can we draw any other resonance structures? Can we take the same atomic arrangement, in other words? So here's the nitrogen. Let's put an oxygen over here, an oxygen over there, and give me more room. Let me get more room. So nitrogen, oxygen, oxygen, and oxygen. The problem indicates that there are 3 resonance structures. We should be able to draw 3. So let's even take this and let's put that back. Let's put another one down here. Okay, so let's see if we can get 3 of them. Well, Looking at the first one, you got a double bond going to the oxygen to the left. What's so special about that oxygen? Why can't this one get the double bond or that one? So again, think options. This one has the double bond here. Let's see if we can make that a single bond and put the double bond over there. Okay, that would be the other one of the other resonance structures. So the way that you can move electrons around is you can use your arrow formalism. Let's take these electrons, let's put them back on the oxygen. And looking at the oxygen on the right, let's take one of its lone pairs and use it to make a double bond. Okay, now we can fill everybody in. So the oxygen over here will have 3 lone pairs now in a single bond. And then the one over there will have a double bond and 2 lone pairs. And the one down here still looks like that. We didn't do anything. And that's a good resonance structure as well. It's negatively charged, so we can give it that double arrow formalism. And let's see if we can do the third one. Hopefully you can see what we're going to do to get the third one. And you guessed it, the double bond is going to go to the oxygen at the bottom. So the way we can do the arrow formalism, let's take these, let's put them back over here. Okay, go back there, and then some of these will come down to form a double bond. And then finishing the structure. This one still looks like that. We didn't touch that. This one has a single bond again with 3 lone pairs, and this one gets the double bond. And there you go. There are the 3 resonance structures for nitrate.